Alright, so we're going to talk about trigonometric substitution. It's very similar in respects to a U substitution. Instead of using the letter U, we're going to use a trig function as a substitution. So the idea is, if you get an integral, which is kind of in the form that you see here, where you've got some kind of a square root of a squared minus x squared, or as you can see in the expressions below, they've got different varieties, of those. We're going to use a trig substitution to be able to solve these integrals, and it does actually make it easier if you can get it in one of these forms. So I'm going to give you the substitution that you're going to use if you see a certain expression. Then I'm going to give you the identity that's going to be very useful in solving that. And after we do a couple of examples, you'll quickly see why it is that we're going to be doing what we're doing. So the first trig substitution that we're going to use is if you see the square root of a squared minus x squared, or you can get it into that form, you're going to use the substitution that x is going to equal a sine of theta. And the identity that's going to go with that, and all three of these identities that we're going to be using come from the Pythagorean identities, comes from the sine squared of theta plus cosine squared of theta equals 1. We're just going to rearrange that, and we're going to say that cosine squared of theta equals 1 minus sine squared of theta. And again, you'll see why it's useful to have it in that specific form. You don't have to memorize it in that form. If you've got the square root of a squared plus x squared, we're going to use the substitution x equals a tangent theta. And the trig identity that one comes from is 1 plus tangent squared of theta equals secant squared of theta. So secant squared of theta is 1 plus tangent squared theta. And then the last one, which looks very similar to the first one, just that the x squared and a squared are reversed, and of course it's subtraction, so it does make a difference, is x equals a secant theta. And we're going to use really the same exact trig identity as we did in the one right above that. I'm just going to rearrange it to solve that for tangent squared. So then, of course, tangent squared theta would be secant squared theta minus 1. This is pretty much all you need to know as far as the substitutions themselves and the identities. The problems that we're going to be doing can take a bit of time to do, so we're going to do this in probably 2 videos. We'll do the first 4 examples, I believe, in this one, and then probably the last 3, because the last 2 problems actually are relatively lengthy. There's some tricks to that. What I will tell you is pretty much you're going to be reintroduced to a lot of your trig identities, and then there's a bunch of algebra and stuff that goes into these. A couple of things that we're going to see are going to be a little tricky, a little ingenuity to get them solved. Alright, so the first example, we want to do the integral of square root of 9 minus x squared all over x squared dx. Excuse me. So hopefully you can see that the trig substitution that we're going to do here is going to be in the form of the a squared minus x squared. So the trig sub that we'll do is going to be our a sine of theta. Now a is going to be 3 because a squared is 9 in this case. So x is going to be 3 sine of theta. And for this specific problem, I'm going to go ahead and write out a bunch of different steps that I wouldn't normally write out. I would assume that you guys can figure some of those things out. But this one I will write out every step as much as I can. So in this case, we're going to go ahead and replace all the x's with 3 sine theta. So we'll have the integral of the square root of 9 minus, now if I replace x with 3 sine theta, that would give me 9 sine squared theta over x squared, which once again, squaring x is going to give me 9 sine squared theta. Now the problem is I still have this dx to deal with off to the right hand side here. Everything is now in terms of theta in my integral, So we're going to have to figure out how to get rid of that dx. Well, we're going to have to take the derivative of our trig sub. So dx here is going to be the derivative of 3 sine theta, which is 3 cosine theta d theta. So that's what's going to go in for my dx over here. So we'll have to multiply that by 3 cosine theta d theta. All right, well, you might look at that and think this thing does not look that much better as it is, and it doesn't right now, but it will. So let's do a little simplification. What I see is that within the square root I have a 9 in common. I'm going to factor that 9 out, which will leave us with 1 minus sine squared theta over 9 sine squared theta 3 cosine theta d theta. Oops, forgot a parentheses there. Alright, hopefully you'll see a couple of things in here. I've got this 9 right here, which is now multiplied by the parentheses, which means I can now take the square root of the 9 out to the front. So I can take a 3 out to the front of that square root, which will leave me with the square root of 1 minus sine squared theta on the inside. Just rewriting the rest of this. And then, whoops. And then what you should see is that I've got 1 minus sine squared theta on the inside of the square root. Well, 1 minus sine squared from the identity that we showed on the previous page is cosine squared. And then, of course, the square root of cosine squared, and here I will write this, oops. So this gives us the square root of cosine squared, and as you should probably already have figured out, that's just going to give me cosine on top. So, what we've got now is the integral of 3 cosine theta over 9 sine squared theta times 3 cosine theta d theta. And you should be able to see that the 3's are going to multiply together, the cosines are going to multiply together. So multiplying that stuff together is going to give us, well, first of all, the 3's are going to multiply on top and get 9, so all this is going to cancel out. That's going to leave me with cosine squared theta over sine squared theta d theta. And hopefully you remember from your trig identities that cosine over sine is cotangent, so this is going to give us the integral of cotangent squared theta d theta. Now that is not one of the standard 6 trig derivatives to take an antiderivative of, but I can go back to a Pythagorean identity that has cotangent squared in it, and we didn't write this one down on the other page, but you can easily figure this one out if you go back to your sine squared plus cosine squared equals 1. We can get to the identity that has cotangent squared in it, and cotangent squared is equivalent to cosecant squared theta minus 1. So those two things are equivalent. This is equivalent to that. And cosecant squared is something that I now know the antiderivative of. That is one of the 6, well, it's close. We have to throw a negative out in front. It's one of the 6 antiderivatives that we can do easily, because the antiderivative of cosecant squared is negative cotangent theta. So the antiderivative is negative cotangent theta. The antiderivative of negative 1 is minus theta and plus c. Now it would be really, really wonderful if this was the final answer, and it's not, unfortunately, because what you can see is that we started off with this in terms of x, not in terms of theta. As you can see up here, everything was in terms of x, not in terms of theta. So we have to change those back into terms of x. So in order to do that, what we need to do is go back to our original trig substitution, and if I realize that I can solve that for sine of theta, whoops, jumped way too far ahead. Sorry about that. Still working out some of the technical difficulties here. There we go. So I can solve this for x. I'm trying to anyway. There we go. I'm sorry, I can solve this for sine of theta. So sine of theta is going to be x over 3. And why do you say that helps? Well, I do eventually need to solve for theta. As you can see, boy, I'm really trying to work this out. As you can see, I'm going to need theta down here. So I do need to solve that for theta. So if I solve this for theta, theta is simply going to be the inverse sine of x over 3. But I also need to solve this thing for cotangent of theta. And yes, I could just plug that inverse sine of x over 3 into the theta down here and get cotangent of an inverse sine. I prefer not to do that though. So let's go ahead and figure this thing out the way it's supposed to be. What we need to do is we need to go back to the general idea of a right triangle. And if this is our angle theta, and I know that sine of theta is x over 3, and sine is the opposite over the hypotenuse, I know that the opposite side on this triangle must be x, and hypotenuse must be 3. And if I want to find the third side of a right triangle, I just go to Pythagorean theorem, which would be x squared plus whatever the missing side is squared equals 9. If you solve that for x, and this isn't going to be a coincidence in all these, you're going to end up with the square root of 9 minus x squared. I'm sorry, not if you solve it for x, if you solve it for the missing side. Notice that's the same as that part up there. This is going to be the case every time we do this. So now I have all three sides of a right triangle, and I am looking for cotangent of theta. Well, cotangent is the reciprocal of tangent. Tangent itself is opposite over adjacent. So opposite over adjacent. Well, I'm going to flip that over, and I'm going to get adjacent over opposite. So cotangent of theta should be square root of 9 minus x squared over x. So what we get here is the negative square root of 9 minus x squared over x minus, and we just figured out that this theta was the inverse sine of x over 3. Inverse sine of x over 3 plus c. Now I'm not going to take that much time to do the other problems here. I'm going to skip a few of those algebraic steps that hopefully you guys will be able to figure out. But that is the answer with the inverse trig and the trig substitutions. All right. Problem number 2. One of my favorite problems to do, just because of what happens at the end. I just kind of like the realization that we come to here. So what we've got is we want to find the area of the ellipse that's defined by this function over here, or not function, equation over here. So just a reminder, an ellipse, I mean, we all kind of know it looks like the oval. If we want to find the x and y-intercepts, the easiest thing to do is plug 0 in for x or y. If I plug in 0 for y to find the x-intercepts, that goes away. Solving that for x, you'd multiply by a squared on both sides, and then solve for x, so you'd get plus or minus a. So my x-intercepts are going to be at positive and negative a. Same idea, if I want to find the y-intercepts, we're going to plug 0 in for x, and then we would multiply both sides by b squared, take the square root of both sides, so you would get plus or minus b. It should be the same distance away from the origin. Now, how do I know which one is bigger? Well, that's just going to be dependent upon if A or B is bigger, and we don't know that in this case, so I just kind of guessed that the y-axis would be smaller than the x-axis, but it doesn't matter for our purposes here. But our oval pretty much is going to look something like that. Now, it should be symmetric. I didn't do a really good job drawing it, but you get the idea. This is what we're trying to find the area of. So what we need to do is we need to solve this for y, because we need to make this a function of some kind. So really, if we solve this for y, which is going to be a little messy, that's the easiest way to do the problem. So solving for y, let's subtract x squared over a squared from both sides. Got to have to multiply both sides by b squared. And then we'll take the square root. Now, it does not look very pretty, but that is our function. And specifically, we are really only interested in the top half of this thing, and I'll tell you why. The easiest thing to do in this specific problem is going to be to solve for 1/4 of the area of this thing. I want to solve, let's not use yellow, it didn't look good last time. I want to solve for that quarter. What we can do after we solve for that quarter is we can multiply the whole thing by 4, and it's just going to make things a little bit easier. And because of that, I don't need to have to worry about the positive and negative square root. I just need to worry about the positive, because that's the top half of that ellipse. So our function that we're going to be dealing with is y equals b squared 1 minus x squared over a squared. This is what we're going to have to excuse me, this is what we're going to have to integrate. I don't want to integrate it in the specific form that it's in, so let's do a little bit of rearranging here. Oops, I completely forgot. Hopefully you guys caught this. I completely forgot my square roots. There. Now we've got it. I had to take the square root of both sides. So hopefully what you can see is I've got this b squared under the square root. I can take the b out to the front. Alright, I want to rearrange what's on the inside here. I want to combine that as one fraction if I can. It's just going to be easier, and it'll allow me to do a little extra simplification. So in order to do that, I need a common denominator, which of course is a squared. So this will become a squared over a squared minus x squared over a squared. And then I'm going to combine everything that's on the inside as a squared minus x squared over a squared. And why would you want to do that, you might ask yourself? Well, the a squared in the denominator is nothing more than a constant. So I can take the square root of that a squared in the denominator, and I can pull that out to the front as a 1 over a. So I'm left with b over a square root of a squared minus x squared. Now hopefully what you can see is that this is the form that we have on the very top, a squared minus x squared. Specifically, it's in exactly that form. So this is going to be a trig sub. Once again, that trig substitution is going to be a sine theta. And before I even fill the rest of it in, I know I'm going to need to get rid of a dx, so I'm going to solve this thing for dx, and that's going to, take the derivative, so that's going to be a cosine theta d theta. Alright, so now we're to the point where we can actually start to integrate. So I'm going to go ahead and set this integral up as an integral of b over a square root a squared minus x squared. I do know that I'm going to replace the dx, but for right now I'm going to leave that in there. Normally, this thing would go from 0 to a. Okay, so let's go back up here. Oops, let's go back up here and look. It would have gone from 0 to a. And then I'm going to take the integral of the square root. But we want to put this thing into terms of trig, so we're going to have to do a little bit of substitutions. So I'm going to write the integral. Oh, don't forget, have to multiply it by 4, otherwise we'd only come up with a quarter of our answer. So yes, you can pull the b over a out. I'll pull that out in a second, but I'm going to leave it there for right now. I'm going to go ahead and replace this with a squared minus my trig sub, which is x equals a sine theta, so that'll give me a squared sine squared theta. And then our dx is going to be a cosine theta d theta. Alright, and hopefully what you can see is that this a will cancel out that a, so I can pull the b out to the front, which is what I'll do. And then I'm going to have this integral. Thank you for the thunderstorm warning. Appreciate that. Then we're going to have this integral of the square root of a squared minus a squared sine squared. Hopefully you can see that I can take those a squareds, factor that out, pull out the a squared from the square root and have an a on the outside. Then I should be left with 1 minus cosine squared theta if I take the a out to the front, which of course is sine squared. The square root of sine squared is sine. Again, I told you I'm going to start going through the steps a little bit more quickly. I'm sorry, confused myself. It's 1 minus sine squared, which is cosine squared. So I'll have cosine theta. And then I've still got cosine theta d theta over here. So if I kind of rewrite this, and yes, I do realize that I have not put bounds in there yet. We'll do that in a second. If I rewrite this, I can pull the a out to the front. So I've got 4ab integral cosine squared theta d theta. Alright, the bounds. My original bounds were 0 to a. That was in terms of x. I need this in terms of theta. Normally what you would do, and we're going to do the same thing, just got to be careful on what you're plugging the stuff in for, is we're going to come back to this up here to change our bounds into terms of theta. Well, the first thing I have to do is plug 0 in, but I'm plugging 0 in. It is a value of x, so it goes on the left-hand side here. So 0 is a sine theta. Well, you can divide out the a, and then you've got sine theta equals 0, which means, of course, that theta is 0. The other one is if a equals a sine theta. Well, in that case, you can divide out the a's, which leaves you with 1 equals sine theta, and that means that theta then, to give you a sine value of 1, has to be at pi halves. So those are my new bounds. So we're going to go 0 to pi halves. And if you happen to remember your polar coordinates, that should make sense that I'm going from 0 to pi halves. From here up to here sweeps that region 0 to pi halves. So you didn't have to do it the way I did it if you realized that that was the case. Alright, now we're almost ready to integrate. We haven't actually taken an integral yet. We haven't really done any calculus other than writing the integrals down. We need to reduce cosine squared theta. We can reduce cosine squared theta by using the identity that cosine squared is 1/2 1 plus cosine 2 theta d theta. And we'll integrate that from 0 to pi halves. Don't forget the 4a, b in the front. So let's take the 1/2 out to the front. So that's 2ab. And then I've got the integral of 1 plus cosine 2 theta. Well, the antiderivative of 1, of course, is theta. The antiderivative of cosine of 2 theta is 1/2 sine of 2 theta. And we have learned that one. and use that one several times, and we will use that one several times in the future in multivariable calculus. So now we just plug in pi halves. If I plug pi halves into theta, I get 2ab times pi halves plus plugging pi halves into theta for sine actually is going to give me sine of pi, which is 0. And then plugging 0 into theta gives you 0 for both of them. So really we get 2ab times pi halves. The 2's are going to cancel out, which leaves you with pi ab. Now why might you say that I say that this is one of my favorite ones? Well, if you think about it, it's really simple to find the area of an ellipse. If I know A and I know B, which comes straight from the equation, I have the area of an ellipse. So if I just knew what this A and this B value were, just multiply them together times pi. But the really cool thing about that is think about this. If A and B are the same, that means it's the same exact distance from the origin to A that it is to B. This thing becomes a circle. And if A and B are the same, this would become pi a squared, where a is the radius, pi r squared. This is what, of course, we know is the area of a circle. Anyway, I just think that that's kind of cool. I think I'm actually going to stop right here. We're going to come back. This may end up being a 3-video lesson because this one kind of went a little bit longer than I wanted to. So we'll come back and yeah, we'll do examples 3, 4, and 5 probably in one video, and then 6 and 7, the 2 long ones, in the last video.